Hi, AP Calc gang. Last lesson already from chapter 4 on something called related rates. These problems are fairly difficult, but kind of fun too. I think you'll be able to see the practicality of them. So we'll tell you a little bit about them and do about 3 good examples in this little video. So what related rates are, as you might guess, are problems where two rates are changing at the same time. Now this example right here will actually be doing one like this, not on the video but in class. What's actually changing here, of course, is the rate that this person is running away from the light, and the other thing that's changing is the length of his shadow. And so we'll be doing a problem or two related to that. Seems a little bit dorky, but that's what they're all about. Here's how to solve related rates problems. This is just sort of a summary of what types of things you might do. First of all, of course, read the problem, identify all quantities that are changing. So you'll be looking for the two things that are changing. And number 2, write an equation that connects these variables. So a lot of times there will be some familiar formula like area or volume, Pythagorean theorem, similar to triangles. The actual equation is the toughest thing you have to write here. Next, we want to differentiate both sides because that's going to tell us something about the rate. Almost always this will be with respect to time, as we'll see. And of course, what might happen when we do that is we'll have to use that implicit differentiation that we studied about last chapter. Number 4, substitute any known quantities or rates. So the problem might tell you that at a certain time this was going at a certain rate, or the length of this particular side was so and so. So we'll know some of those specific things. The key thing is, first of all, differentiate, then substitute. Sometimes students get these two mixed up, but do the differentiation first. And then lastly, we'll try to solve for the thing we're really trying to find. Usually they'll give you one of the rates and you'll have to solve for the other. Alright, so let's just hop in and try some of these problems. Alright, here's kind of a classic one. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as you can see. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When that radius is 4 feet, at what rate is the total area of the disturbed water changing? Alright, so as you can see, the two things that are changing are the radius of the disturbed water. Of course, that's getting bigger and bigger as we look at those concentric circles. And then obviously the area is also changing. So there are my related rates. Obviously, as that radius gets bigger, so will my area will get bigger as well. Alright, so we want to figure out, well, what is it that we're going to try to write an equation of here? Well, probably it's going to be area. And we remember that the area of a circle is pi r squared. And now what we want to do is the rates that are changing, of course, is the area is changing and also that radius is changing. So now we're going to go ahead and differentiate this. And remember, we say do it with respect to time, so we have dA over dt. Now on the right side here, remember that pi is a constant. So in a sense, I can kind of pull that pi out of there or just include it in my calculations here. So the derivative of r squared, of course, would be 2r. I'm going to just put that 2 out in front there, so it's going to be 2 pi. So 2 pi r. But now here's our implicit differentiation in action. I have to say dr over dt. Now that's a little bit different than what we did before with implicit differentiation, because we usually did it only with y, and with x we actually did our differentiation as normal. But here we have two variables, and since we don't know exactly what a and r are, that's what we want to figure out. Well, we are trying to figure out the rate that the total area is changing, so here's what we're trying to find. Now, can I substitute any other values in place on the right side? Yeah, I think so. 2 pi, of course, is a constant. It says when the radius is 4 feet, so I'm going to put that in place of r. and then it does actually give us this dr over dt. It says that that is changing at a constant rate of 1 foot per second. So I'm going to put 1 in place of that dr over dt. And when I multiply all this out, I get 8 pi. Try to get your correct units in here. So the area, or the units for the area, would be square feet. I'll write it like that, per second. So 8 pi square feet per second, that's my answer to that particular solution. Alright, so there's our first related rates problem in the books. So now let's go on and take a look at a couple more. Alright, so here's one, another kind of a classic one. 25-foot ladder is leaning against a vertical wall. The floor is slightly slippery, and the foot of the ladder slips away from the wall at the rate of 0.2 inches per second. How fast is the top of the ladder sliding down the wall when the top is 20 feet above the floor? Alright, so you have a little diagram here. Always good to do that on these kinds of problems. What kind of equation will relate these things? Well, I think you can see that this is going to be a classic right triangle problem. So I'm going to use the Pythagorean theorem, x squared plus y squared. In this case, we know that that the hypotenuse is going to be 25, so I can just put that in there. 25 times 25 is 625, I think. I hope. Alright, now we're going to do our differentiation. And so we're going to get 2x, and again I have to include that dx over dt in this case, plus 2y, dy over dt, and of course the derivative of 625 is 0. Now I'm going to be able to substitute in some things here. So I know that when y is 20, then I can probably figure out also what x is in this case. Now what I'm really trying to find in this case is how fast it's sliding down the wall. So I'm really trying to solve for this dy over dt. Plus the problem does give us this dx over dt as well. So let's just see if we can plop in all those values here. So I'm going to have I'm going to put in 15 for x, because if it was 20 feet above, if I went ahead and solved this, x would end up to be 15. That's just a variation of a 3, 4, 5 right triangle. So that's where that 15 comes from. And plus 2. Now the y value is also given to us. That's the height, initial height of that ladder is 20. And then this, I should have also put this dx over dt is that 0.2, and that's going in the direction to the right. That's increasing, so I'm going to just, I forgot to get that in there, so that 0.2 should be in there. And then I'm still trying to find my dy over dt, of course. Now if I try solving all this stuff for dy over dt, I can multiply this out. I think I'm going to get, well, let me just do one more step here. 2 times 20 is 40 dy over dt. 2 times 15 is 30. 30 times 0.2 I think is 6. But when I have to subtract it over on that other side, so I'm going to get that. Actually it's going to be so negative 6 there. And then if I divide both sides by 40, my dy over dt will be negative 6/40, and I believe that's approximately equal decimal-wise to negative 0.15 inches per second. Now we might have some little debates about our signage here, and maybe not the biggest thing in the world, but I would suppose technically because this ladder is moving down here that my sign should be negative, because the distance from the ground there is decreasing. If it was going the other way, it'd be positive. For instance, this one, because the ladder is sliding out in this direction, that's why I would say this dx over dt should be that positive 0.2 right there. Alright, so that's kind of another fun problem that we did. Alright, and the last one, and one that we'll see here involves the famous tank problems. So a conical water tank means in the shape of a cone, vertex down, radius of 10 feet at the top, 24 feet high. If water flows out of the tank at a rate of 20 cubic feet per minute, how fast is the depth of the water decreasing when the water is 16 feet deep? Now, a lot of times on these tank problems, it's good to look at them, kind of a cross-section idea, so we can set up some similar triangles. Now, we know from the problem here that the top has a radius of 10 feet, and we also know that the whole height of this thing is going to be 24 feet. So a lot of times what we like to do, especially to connect these two variables, r and h, is we'll do a little proportion here. So do you see that 10 over 24, that would be like the radius over the height, and I can set that equal to the radius of the height. This is supposed to represent like the depth of the water in this particular problem. And once I do that, I can do a little cross multiplying here. So I get that 10h equals 24r. Now the nice part about this is I'll try to solve this for one of these variables. I think in this case I'm going to solve this for r and dividing by 24, so I get r equals 10 24ths times h. You can actually reduce that to 5 12ths h. That's what r is. Now that'll come in handy a little bit later. Now the equation we're going to do here, because we are doing a volume type thing here, this is the volume of the tank, you might remember, I'm going to tell you right now, here's the volume of a cone, 1/3 pi r squared times h. Now notice we really have three different variables here. We have v and r and h. I'd like to whittle that down so I really just have one variable there. And so that's where this solving for r down here comes into play. I'm going to essentially put this r value in place of this one. And so then the only two variables I'll have to worry about are r and the volume then, which is what I need. Alright, so let's go ahead and do that. So I still have my 1/3 pi, but now in place of r I'm going to put that 5 12ths h in there like that. Now that's going to be squared. Here's my other h. Alright, so a little bit complicated here now. Do you see that if I square this, I'm going to have 25. I'm going to still have that pi up there in the numerator. And I'm going to actually have h squared times h, which will give me h to the 3rd power. Meanwhile, in the denominator, 12 is going to be squared, so 12 times 12 is 144. 144 times 3 is 432. So look at that bugger. Now I think I'm going to go to the next slide here when I get to my actual finding the derivative of this, just so I have a little bit more room. So I'm going to do that. Alright, so now when I actually find that derivative, it's going to be 25 pi over 432. All that's h to the 3rd, you might remember. I'm going to find the derivative of this, and by the way, this is what the volume equals. So when I try to find the derivative of that, remember that all of this stuff is a constant or a number. So when I'm going to end up taking 3h squared, but 3 is going to divide into this 432. So what I'm going to actually end up with is still the 25 pi, but then the 432 will kind of be divided by 3, so I'll get that 144, and then it's going to be h squared, and then dh dt. And by the way, all that's going to be equal to dv over dt. Alright, well now I can substitute in a bunch of stuff here. I know that that particular height from that last column that or last slide that I have 25 pi over 144. I'm getting a little bit short of time here, so I'm going to try to consolidate this a little bit. So it's going to be 16 squared, this dH over dt. That's what I'm looking for. And it does tell me that the volume is flowing out at a rate of -20. So I can substitute that in place of dV over dt. Actually then, when I combine all this stuff, we'll do more of this in class or be a little bit more specific, that when I solve all this for this dH over dt, I'm going to end up with -0.143 feet per minute. And that's how fast that height is going to be decreasing in this particular situation. Now, these are typically pretty tough problems. We'll do some more of these in class so you get a better feel for these, but that gives you some good examples of related rates. Thanks for watching. We'll see you guys in class.